All right, engineering physics. This is the last week, and we're working on thermal processes, just finishing up the engineering thermodynamics section. And the big goal today is to try to put our first law of thermodynamics into action, try to figure out the changes in work or changes in internal energy in a piston that's involved in an engine. So what are the thermodynamic properties of pistons when they expand and when they absorb heat? So just to remind us that the change of internal energy is equal to my change in heat in my system minus the change in work done by the system on the surroundings, okay? That's that first law of thermodynamics that we worked with in the last episode, okay? And today, we're going to be talking a lot about piston systems, modeling a simple gas system that we use in our combustion engines to do work, okay, to move things. And also in your text, you'll see that they often talk about the piston systems when you're thinking about thermodynamic processes. Okay, another thing we're going to be talking about are these thermal processes in specific: isothermal processes, isochoric, adiabatic, and isobaric processes. We need to be able to recognize what they look like in a graph form. Okay, so this diagram over here just shows a very typical process of how we can convert heat energy into work using a gas piston. Okay, this is your piston, that's the piston walls, that's a load, a mass, that's your piston head, and here's the sealed gas inside. So in step number one, if I heat up that gas, okay, that gas will expand based on gas laws, and pressure times my change in volume, as I showed in the last episode, is equal to the work being done. Okay, so if that heat energy goes into changing my volume, and I can know my pressure in the system, I can calculate the amount of work that I did to move that mass. Okay, and then if I move that load off and cool the gas, this is important, then that piston is able to compress, and then the outside, the external, either energy would be removed from the system, or work would be done to compress that piston to come back to its reset position. Okay, so this diagram kind of shows a very important principle that we talk about in terms of engines. No engine can be 100% energy efficient, and we talked about that in the power unit, that no process, no energy generator can be 100% efficient, because what we have to do is we have to reset the system back to its beginning state. Okay, and in resetting that, energy has to be dissipated. Okay, and that's a good example. So we've already talked about that before. Okay, so, but there's different ways that that piston can expand, and there's different ways in which that energy can be transferred, and that's using these different thermal processes. So anyone who's trying to design an engine wants to make the engine as energy efficient as possible. It's not going to be 100%, but we might be able to make it much more than 40 or 50%. That would be excellent. If we're able to do that, then we can make a much more energy efficient car, and these would be things that, you know, maybe a few of you be interested in if you're looking at designing formula racing cars that have a limited amount of fuel for a race. We want to make that engine as efficient as possible. Okay, so something that you're going to see in the text is PV curves. PV curves. Okay, when we're looking at what's happening in these pistons, we will model the pressure, the changes in pressure, and the changes in volume. Why? Because if you multiply pressure by the change in volume, that'll give you the work being done. Okay, now in this whole system, that is a cycle. So we would be able to monitor the change in pressure and volume in that cycle and make a cyclical graph on a PV graph. What is happening to the pressure and the volume as that whole piston is going through its process? And there's 4 different things that can happen, okay? These blue lines that you see over here, I'll talk about in a little bit more detail, but those are called isotherms. Isotherms mean that the temperature inside the piston is constant. Okay, it doesn't change. So if heat was added, the temperature always remains constant. Okay, and then these PV curves follow our gas laws. PV equals nRT. So as long as the amount of gas that I put inside of my piston, N, is constant, and R is the universal gas law constant, and if the temperature doesn't change, if I'm following an isotherm, then P and V are going to be inversely proportional. We've done that so many times in gas laws, okay? So that would be your classic PV curve for the gas law at that temperature. Now, if I did the experiment at a colder temperature, of course, my pressure, that state is going to be different. the temperature, the state of that gas will be different because it's now colder. Okay, so the pressures would be smaller for those volumes, and if I cool it, the pressure would be even smaller for those volumes. Okay, so those blue lines are isotherms, and then in this process, I can change the position of the piston in many different ways. Okay, I can change the position of the piston, change the volume of that piston in an isobaric process, which means that I'm not changing the pressure is constant. I can change the pressure of the system without changing volume. That's an isochoric process. I can change the volume at a constant temperature. That's my isothermal, as I described before. And I can change the pressure and volume at the same time by changing the temperature of the system. That's an adiabatic process. Okay, so we're going to learn, the whole point of today's lesson is to learn in specific what those processes look like and be able to explain how to calculate the work being done or the work done on the system in those types of processes. Okay, so the first concept, just to remind us, how does an isothermal process work inside of a piston, not in PV equals nRT? Okay, well, what you'll see here is that you have a candle that's supplying heat, and that heat is going into my piston, into the gas inside of the piston. And like I said before, in order for that pressure not to change, or the in order for the temperature not to change, because the temperature in an isothermal process is constant. So temperature is constant, okay? In order for my temperature to stay constant, what I have to be able to do is that gas immediately has to transfer its energy to that piston. That head has to have very little friction, okay? So that heat energy going in immediately causes a volume change without changing the temperature, okay? And then that system will follow an isothermal process that looks like that. That's for that specific temperature. If the temperature of the gas started at a hotter temperature and remained that way, then my isotherm would look a little bit higher up like that, okay? Those are different isotherms. That's how we describe that. Those are called isotherms. Each one of those graphs is a different isotherm for that particular gas in the cylinder, okay? So just to explain again, there has to be very low friction, and the heat that goes in immediately goes into changing the volume. So what does that look like in our first law of thermodynamics formula? Okay, well, delta U is equal to delta Q plus delta W. So the question I ask here is the internal energy of this gas changing? Well, the internal energy of the gas is equal to 3/2 nRT. And I can say that the change in internal energy would be the change in the temperature of the gas. Since there's no change in temperature, okay, my change in internal energy is going to be 0. Okay, that's important for a isothermal process. There is no internal energy change in that gas. In that case, if that's true, then what ends up happening is my negative change in W is going to be equal to the change in Q. So the amount of heat that is put in is going to be equal to the amount of work done in a system. Okay, now an important thing that we're going to have to figure out is what is the sign for delta Q of a system, okay, if heat is going in or if heat is going out. Is it positive if heat is going in, or is it negative if heat is going in? I'm not going to answer that. I want you to look in your text, and also you can try to figure it out from here. If it's positive work, that means work is being done by the system on the surroundings. Okay, if it's negative work, that means that the surroundings are doing work on the system. Okay, so this might be able to answer what delta Q must be if heat is going in or if heat is coming out. Okay, all right, so that's an easy way of understanding. If I could measure the amount of heat that I put into the system, I'd be able to measure the amount of work that it can be done in an isothermal process. All right, the next thing that we're going to talk about are isobaric processes. An isobaric process means I have constant pressure. Okay, so the piston is moving at a constant pressure. And what that looks like here, I have a diagram a little bit below. Here's a piston, the heat is coming into the piston at V1, okay, and then that piston is expanding because heat went in, okay? But the pressure inside always stays constant. And that makes sense because in this system, you got atmospheric pressure on the outside. Okay, so that's atmospheric pressure is pushing on the piston on that side, and then the gas inside is pushing on that side of the piston. When you heat it up, the pressure is going to go up inside of the gas, but if that piston again has very low friction, it's going to want to equilibrate. Okay, if it's very low friction on those walls, as the pressure starts to go up, there's an equilibrium is going to be made. Okay, remember pressure is force divided by area. So the force here is going to be greater than the force there. So it's going to push that piston out and try to maintain the pressure constant inside. Okay, so in an isobaric process, the piston immediately expands when heat goes in. Okay, but what if I had a thermometer in there, I would see that the temperature of the gas would change because the temperature is what's causing the pressure to increase. Okay, so what we can see here is in an isobaric system, okay, the pressure is here, okay, and it stays constant, it's flat, but what doesn't stay constant is the fact that the graph has gone from one isotherm to another isotherm, okay, which means that there has been a change in temperature in the system, okay. If there's a change in temperature of the system, that must mean that my delta U is positive, okay. I've increased the internal energy because I've changed the temperature of the system. So looking at this, delta U is equal to delta Q plus delta W, okay? We can try to figure out how to calculate the work being done, okay? So how would I look at this graph and try to figure out how much work was being done by the system on the environment? Well, that's not so difficult because the pressure stays constant and the change in volume is here. So work, the change in work is going to be equal to pressure times the change in volume. All right. Okay, and I can measure the amount of heat that I put in, or I can measure the change in my internal energy just by looking at the change in temperature. Okay, so my change in internal energy is going to be equal to 3 halves nR T2 minus T1. Okay, and putting that together, I could then do something and calculate the change in heat that was responsible for that type of isobaric expansion. So isobaric expansions are very easy to calculate the amount of work that was done, because if I just looked at the area under that graph here, the area there corresponds to the work being done as I'm putting energy into the system. Okay, so that's an isobaric process. Okay, the next process is an isochoric process. And in an isochoric process, the volume is constant. So what does that look like? So imagine I had a fuel inside here, and the fire ignites the fuel. That's an instantaneous release of heat. Okay, well, that instantaneous release of heat would rapidly increase the pressure inside here, and the piston doesn't have a chance to move yet. Okay, so what would happen is that at that volume, without the piston having a chance to move, the pressure would skyrocket and it would go up over here. Okay, now no work has been done yet, but right now I could see that the heat that went in caused a change in pressure. Okay, now if I was to take a look at the PV graph for that, okay, so I'm here and I'm here. This is T1, T2. And if I jumped there, okay, I've changed isotherms. So although the volume hasn't changed, if the volume hasn't changed, then my change in work is going to be equal to 0. So if I look at the first law of thermodynamics, the change in internal energy is equal to the change in Q plus the change in W. Well, the W cancels out. So in this case, the change in internal energy of my gas is going to be equal to only the amount of heat that I put in. And you'll see later on when we talk about engines, when an isochoric process can be very beneficial at harnessing a lot of work being done. Okay? All right, and here's an example of a thermodynamic cycle. Okay? So if I put If I started here, all right, and I ignited a gas inside and it quickly changed isotherms and went up over here, what I'm doing is I'm loading the system with more potential for work. If it was just isobaric over here, like I showed you before, that area under the curve there would be the only amount of work that I could do. But here, with an explosion and then an isothermal expansion, I have increased the area under that curve. I can generate more work under that situation if I do an explosion inside of a piston, okay? And that's kind of how a combustion engine, that's kind of how all our, whether it's diesel or combustion engine, that's kind of how they work, to increase the amount of area under there. Okay, so that's kind of the goal for all engines, is increasing the amount of work I can do in each cycle, all right? So here would be an isochoric expansion. This is an isothermal expansion, okay? So the isochoric expansion increased the pressure and increased the internal energies, the temperature is higher, and then the system then responds. The piston starts to move with low friction and respond, okay? And then in order to get the system to come back, this is the part where we're going to be losing quite a bit of energy, because I have to lose heat energy quickly. So maybe a vent in the piston is going to open and release that heat. And then the bulkhead of the piston is going to contract isothermally, and then another explosion, okay? And so the area under inside this box corresponds to the amount of work being done in the engine. Because if you think about it, okay, the area here, the area underneath this part of the curve, is the amount of work that the environment is putting back on the system to reset it. Okay, that's by cooling it and squeezing the bulkhead back down again. So all that would be lost energy. And then the front part, all the total area under here would have been the work done in the combustion, but then we have to subtract that part to reset the piston back to its original form. Okay, and here is the last process where we talk about adiabatic processes. I used to have one of these fire pistons in the classroom because it's a cool way of generating a fire and demonstrating thermodynamic cycles. But one of the students who was really strong from pounding fufu all the time was able to break it within 1 second of smashing it. He hit it way too hard. If you take cotton and you put cotton inside this tube, and this tube you can see is very insulated from the outside world. Okay, so no heat from the outside world can get in and no heat from inside can get out. If you smash that piston down very, very fast, you're going to be supplying a lot of kinetic energy to the particles inside of that tube. And that means that the internal energy of the gas in that tube is going to raise very, very quickly. So the temperature inside that tube can become very, 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 very hot. And if you had cotton in there, that cotton would ignite and you create fire. Okay, and that's kind of the principle of a diesel engine. Actually, some survivalists in nature, rather than using a spark, would use adiabatic contraction to start a fire. Okay, and I've seen some survival shows where they've done that. So how does that work? So in an adiabatic process, what you have to understand is it's insulated. Okay, so if an adiabatic piston is insulated, no heat can go in or out. That means my delta Q is equal to 0. So if I look at my first law of thermodynamics, my delta U is equal to delta Q plus delta W, okay? My delta Q is 0, so that means the change in internal energy corresponds to the change in work, okay? All right, and that's pretty fascinating. So if I do work on the system, I'm going to be putting internal energy in the system. If I do negative work, I'm going to be able to remove the heat from the system, okay? And so that's pretty neat. So by me compressing it, I'm doing work from the outside and putting that into the system, which is going to change the internal energy of the gas inside of the system and raise its temperature. Okay, and then on the other hand, we can use adiabatic expansion to cool gases. So if I had a gas starting in this state and I pulled on that piston very, very quickly, what I would do is I would cause a change in the isotherm. Okay, so it would go from one isotherm to another isotherm, and the gas inside would cool, and that's how a refrigerator works. We use a motor to quickly pull a piston out and expand it, causing a cooling effect of the gas. So because no heat can be transferred in and out, the gas itself has lost temperature. It had to use energy inside it effectively to move that piston out. Okay, even though we're pulling it. Okay, we're tricking it and we're making the internal energy of the gas go down. Okay, so adiabatic expansion is for cooling. Okay, and that's how a refrigerator is going to work. Okay, so for adiabatic processes, all right, there's some formulas that you have in your textbook. Okay, I'm just going to erase this stuff. Okay, so you have some formulas in your textbook that we can calculate the change in temperature as a result of rapid compression or expansion. Now remember, it's insulated, no heat can come in or out. Okay, and so those formulas look like this. Okay, you have a formula that says P1 V1 to the power of 5/3 is equal to P2 V2 to the power of 5/3. Okay, so if I knew the initial pressure of the gas inside the cylinder and the initial volume, and I pushed down to, let's say, 1/3 the volume over here, okay, I'd be able to calculate the new pressure inside of that system in an adiabatic process using that formula. And that formula really is being used to correlate to this one, which your textbook shows the derivation. And I'm not going to go through that because I don't think it's that important at this stage. But just knowing that these formulas exist kind of reinforces why a piece of cotton will ignite in there, okay? So if I start my gas at an initial temperature inside of that tube and an initial volume, and I decrease the volume to 1/3, you can see that the temperature is going to compensate by going up, okay? And it would go up very rapidly. And if I do that very fast, the temperature goes up very rapidly. There's no time for that heat to escape with the environment, and I can ignite a piece of cotton in there, okay? So these are two formulas to play with. There's some practice problems in there so that you can play with adiabatic processes, expansion and contraction, okay? Now, the last thing that we're going to talk about, and I'm going to save it for the next little video because this is a long one, is we're going to talk about thermodynamic cycles and how to calculate the energy inside of the cycle. And then one of the most theoretical, efficient ways of generating power or work in an engine is called the Carnot cycle. So that's going to be in the next video.